Welcome to this explainer. Okay, today we're going to completely demystify operations on real numbers and radical terms. If looking at an equation packed with square roots and numbers makes your head spin, honestly, stick with me. I'm going to prove that you already have all the math tools you need to solve them, literally just sitting right there in your brain.
So here's our game plan for today. We're going to cover meet the radical terms, adding and subtracting, multiplying and dividing, rationalizing the denominator, properties of real numbers, and finally, putting it all together.
All right, section 1, meet the radical terms. We really can't solve the puzzle if we don't know what pieces we're working with, right? Let's dive in. First up, a super important definition. In algebra, we always talk about like terms. Well, in the radical world, like radical terms are simply terms that share the exact same index and the exact same radicand. If they've got those two things in common, boom, they're a match. Let's actually break down the anatomy here so these vocab words make sense. Notice how that little number is sitting outside on the ledge of the root sign? That's our index, in this case, a 3. The number tucked safely inside under the root is our radicand. Here, it's a 2. And that big number out front? Yep, that's our radical coefficient.
Now, comparing these side by side, it's pretty easy to see this rule in action. 5 cube root of 2 and negative 3 cube root of 2. Those are like radicals because, well, the index and radicand match perfectly. But if a term has a different index, say a square root versus a cube root, or a totally different radicand, they're unlike. They simply can't be combined. Think of it like a VIP club, right? Only matchy numbers get to hang out together. Moving right along to section 2, adding and subtracting radicals. Let's start combining those like terms and building up our toolkit.
Okay, here is the absolute golden rule. If you are comfortable adding basic algebra, you already know how to add radicals. Seriously, it's that straightforward. We treat like radical terms exactly like we treat like algebraic terms. This actually perfectly illustrates that golden rule. Look at the top equation. Just as 8x plus 3x gives us a total of 11x, we can do the exact same thing on the bottom. 5 root 3 plus 3 root 3 is simply 8 root 3. You literally just add the outside coefficients, the 5 and the 3, and the radical part, the root 3, stays exactly the same, just like the x did.
Next up, section 3, multiplying and dividing radicals. Now for this one, it's all about matching placement.
The secret code here, matching placement. When you're multiplying or dividing radical terms, you just multiply or divide the coefficients on the outside together, and you do the exact same for the radicands on the inside. Basically, outsides with outsides, insides with insides.
Let's step through an example. We have 4 root 3 multiplied by negative root 3. We multiply our outside coefficient of 4 by that invisible outside negative 1, giving us negative 4. Then we multiply the inside 3's together. The square root of 3 times the square root of 3 just gives us a regular whole 3. So multiply that negative 4 by 3, and it cleanly simplifies down to negative 12. See how nicely that just collapses?
Well, that's all well and good when numbers are acting nicely on a single line, but it brings up a really fascinating question. How do we handle a fraction when there's a messy, complicated radical stuck at the bottom in the denominator? Math convention says we really don't like leaving radicals down there.
Which brings us to section 4, rationalizing the denominator. Let's look at how to ensure there are no radicals downstairs. This is honestly one of the most empowering techniques in algebra.
To rescue our fraction and get that radical out of the basement, we just follow 3 super satisfying steps to magically turn that bottom radical into a friendly whole integer. First, identify the offending radical. Second, multiply both the top and the bottom by that exact same radical. And third, just simplify.
Let's see this in practice with 9 divided by the square root of 3. See? Not so bad, right? Because multiplying the top and bottom by root 3 transforms the bottom, root 3 times root 3, into a solid whole integer of 3. On top, we get 9 root 3. And, letting us simplify the whole expression beautifully, we just divide the outside 9 by the bottom 3, leaving us with a final clean answer of 3 root 3. No more fractions.
All right, section 5, properties of real numbers. It's time to take a quick step back and reveal the overarching rules of the math universe. This table is basically your ultimate cheat sheet. It proves that radical operations perfectly obey the exact same rules as regular real numbers. The commutative property? That just means the order doesn't matter when adding or multiplying. A plus B is the same as B plus A. The associative property? How you group them in parentheses doesn't change the outcome at all. From the distributive property to identities and inverses, radicals play by the exact same rules you already learned in standard arithmetic. Finally, section 6, putting it all together. It's time to hit the boss level and really flex Joe's new math muscles. Just follow the bright red arrows to distribute the outside term to everything inside the parentheses, step by step. 2 root 3 times 5 root 3 gives us 10 times 3, which is 30. Then 2 root 3 times negative 4 gives us negative 8 root 3. So our final answer is simply 30 minus 8 root 3. And when you're facing two binomials multiplied together, it's really just more of the same. We use our trusty distributive property to multiply absolutely everything out. The 2 gets multiplied by the root 3 and the 7. The root 3 gets multiplied by the root 3 and the 7. Once the whole shebang is expanded out, we use our commutative property to shift things around, group the like terms together at the end, and that gives us 9 root 3 plus 17. But best of all, your absolute favorite algebraic shortcuts still work perfectly here. Take a look at this kind of intimidating problem. 7 root 2 minus 5 multiplied by 7 root 2 plus 5. If you recognize this as a difference of squares, where x minus y times x plus y equals x squared minus y squared, you can literally just plug in the formula. Square the first term to get 49 times 2, which is 98. Square the second term to get 25. 98 minus 25, and watch that huge, complicated problem melt away into a simple, beautiful 73. By realizing that treating radical expressions is exactly like treating basic algebra, you've unlocked a massive mathematical superpower. You didn't need a whole new set of rules. You just needed to see how the old ones apply here. You know how to identify like terms, you know how to rationalize denominators, and you definitely know how to expand binomials. So the only question left is, what complex radical-filled equation are you going to conquer next?